So we've just finished up talking about the property of inertia, how lazy an object is, how hard it is to get it to change what it's doing, either being at rest or in motion. And changing your at rest or in motion state is an acceleration. So clearly mass has an effect on acceleration. We also expect that how hard you're pushing or pulling, in other words, the force that you're putting on the object, is going to have an effect on its acceleration too. And in this lab, we're going to carry out two kind of mini experiments to test the effect of both of these variables. We have to consider them both to be separate independent variables that we're going to change. We want to see how they affect the dependent variable of acceleration. And what that means is that we're going to carry them out one at a time. So I want to show you the overall experiment that we're going to be doing, and then we'll talk about what the general strategy is for controlling first one variable and then the other. So the basic experiment we're going to have is we're going to have somebody pull another person down the hallway on this low friction cart. These are rollerblade wheels, so we can keep the force of friction as negligible as possible. We're going to be able to measure the force people are pulling because we've got this old fish scale, which can measure up to a 30-pound pull. So in one of the experiments, as we discussed, we'll be keeping the mass of the person constant and pulling with different forces. In the other, we'll do the opposite. We'll keep the force constant and we'll pull people of different masses. So I want to show what one such pull looks like. And my friend Mr. Sember helped me do it. Hang on one second. So Mr. Sember has volunteered to pull me, and he's going to pull me at a constant force of 10 pounds, and we'll see what constant acceleration looks like.
Whee!
So on the next slide, you're going to see some data from one of my classes of how mass affected acceleration, and then you'll see a graph, and we'll take a look at what that quality looks like. So I hope you can see how we're going to have a control over these variables. We actually have a whole class full of people, so we could have different people ride the cart, and we could also have one person pull the cart with different forces. Again, we can only change one independent variable at a time, or else we don't know what is causing the effect. So we're going to start by changing the mass of the person riding the cart and seeing how that affects acceleration. In order to control force, we're going to pull with 10 pounds constantly. So basically, we're going to get 5 or 6 people. We're going to have their weight and use that to get their mass. And then we're going to go back in the hallway. The hallways at our school are a lot like a football field. They're striped, so we can use that to figure out how far someone's traveled. And we can use a stopwatch to get time. So we'll just plug into our constant acceleration equation and we'll solve for acceleration. So by getting people's weight, the distance they travel and the time they travel, we get all the information we need to test mass versus acceleration. So here's our data for acceleration versus mass for one of the classes in the 2017-2018 school year. And you can see that both a line, which I drew in pink, and a curve actually could be described to fit the data pretty well. There's nothing that makes this obviously nonlinear. So what I had the class do was draw a best fit line and then discuss what would it mean to have this line cross the M axis here. Well, that would imply that when you had a large enough person, when your mass got to a certain level, your acceleration would suddenly become negative. So that would imply that if you had like something twice as massive as the largest object, that all of a sudden it would start accelerating backwards when the person grabbed the scale. And that clearly doesn't make any sense. As students in most classes pointed out, it would make sense that the bigger they got, the less acceleration they had, and that pattern would continue rather indefinitely. Usually a student pointed out that mathematically we would call that an asymptote. That zero acceleration we'd expect to be the most negative acceleration, and that the larger you got, the closer you get to it. So we went through graphs that could fit that pattern, and the hyperbola, which is sometimes called the rational graph, seemed to be the one that fit the best. Usually we think of that as y equals 1 over x, but it's really y equals any value over x. And usually we would abbreviate that any value with a k for constant. So on this graph, what we're seeing is that acceleration is equal to some number divided by mass. And that another way of saying that is that acceleration is proportional to mass. So that's one of the big ideas of this lab. And what it can be translated into is that as mass gets bigger, acceleration gets smaller. Because if you have a bigger number on the bottom of a fraction, that makes the overall fraction smaller. So we're going to try to analyze that hyperbola, or that rational graph, to try to figure out if we can get some important information out of it. The problem with a hyperbola is that most spreadsheet programs can't fit to it, and that's actually true of a lot of the functions we're going to want to study, especially in the college level physics classes. So we have to have a technique to transform the data into something we can work with. And we're going to use a technique called linearization. So I want to walk you through it for this particular lab, and we will hit it again and again and again as we go forward. Just one thing to understand, y equals mx plus b, our slope-intercept form for a line. From here on out, I'm going to write it y equals kx plus b, k for constant. And it's just that we're using m for mass. So this doesn't look as familiar, but I think it'll stop us from being confused. Here's some data from one of my periods in 2016-2017. As we saw from the previous data, which is really typical for a class, it's not easy to tell that it's a hyperbola. And that has to do with how hard it is to collect this data. But this particular class during that school year did a very, very careful job. And we'll have some evidence for how careful they were later. But it's not hard to imagine that that could be a hyperbola. So we're going to use this data because it's going to help us make more sense of things. We expect this to be of the form A is proportional to 1 over m. As mass gets bigger, acceleration drops. And that means we have the equation A equals k over m. There's a proportionality constant. There's some number k here, but the big idea is that as m gets bigger, A is going to get smaller. I'm just factoring out the k, so I'm writing A equals k times 1 over m. Now, why would I do that? What's useful about that? If I factor that k out, A equals k over m becomes A equals k times 1 over m. And that makes it really easy to line up against the slope-intercept form of the line equation. X kind of takes the role of 1 over m. Y takes the role of A. And then we're left with the slope just being the slope. The fact that these line up so nicely together tells us something amazing. If we treat 1 over m as our x-axis and A as our y-axis, we should get a line, even though our original graph with mass on the x-axis gave us a curve. So this is transforming our data to make something that the spreadsheet program and us can't fit into a new equation, a line, that we can fit very easily. So what is 1 over m? It's literally just 1 divided by the mass. So I'm telling the spreadsheet to copy the masses down, but instead of writing them exactly, do equals 1 divided by the original mass. That's going to get me the inverse mass. Acceleration, I literally just copied down. And if this is really a hyperbola, then if we graph A versus 1 over m, it should be a line, according to the fact these line up together. So we do that. And we get something that looks really linear. And it has a slope of 47.82. So we'll see if that number makes any sense to us. But there's no way we could have got it from the original graph. Mass versus acceleration is hyperbola. Spreadsheets can't fit hyperbolas. But this linearized data, we get that constant out of there. And that constant may be very important to us. And we're going to try to figure out what it is. So this is a trick we're going to use all the time when we have complicated functions. in order to get a fit when mathematically we can't otherwise. So just to recap, we expect acceleration is proportional to 1 over mass. That's the same thing as saying some number k divided by mass is equal to acceleration. If we factor out a k, we see that plotting 1 over m versus a should give us a line, and the slope of that line should be k, the constant. So remembering that our slope was about 48, we got to ask ourselves, have we ever seen that 48 somewhere? We have. It's really close to the force that we pulled with. Remember, we pulled with a 10-pound force, and 10 pounds in newtons is about 45 newtons. And apparently this class was very consistent with how hard they pulled, more than any other class I've ever seen. So the slope is the force we pulled with. And if you combine the stuff back together, you get F over m equals a. And that is a very important equation known as Newton's second law, usually written F equals ma. But what it tells us is that the more force we have, the more acceleration. The more mass we have, the less acceleration. So this is one of the most fundamental laws of physics, and we're going to use it to see the relationship between motion and acceleration, how hard we're pulling, and inertia. It's a really big deal equation. I wanted to do one quick last look at just a standard class. So this is a class from the 2017-2018 school year. The hyperbola is not as clear here. It could be roughly linear. When we do the inverse mass versus acceleration, we get a constant that's way off of the 45 that we expect. So that's our other evidence that that one class did a very careful job. The fact that they got a constant roughly equal to the force we were supposed to be pulling with shows that their data is more in line with what we intended to do in the lab. Based on the data we just analyzed, we didn't really need to check the relationship between force and acceleration because we saw that the slope of the a versus 1 over m graph was the force. But for completeness, here's some data where we pulled the same student with an increasing force between 4 and 12 pounds. And if we graph the force versus the acceleration, we see a linear trend. So force really is directly proportional to acceleration. So that's further evidence that force belongs on the top of that fraction, as we saw from the previous analysis.